Hi everyone. As Michael presented me, I'm Pedro Galvez. I'm a PhD student at the University of Bristol, and today I'm going to talk about the work that we've done regarding the phase segmentation of uncured composite prepregs using deep learning. So I will start by giving a short introduction about what prepregs are, then describe what methods we have to separate the different phases in prepreg composites, specifically using deep learning and compare the results to thresholding. Then I will present some results about how the architecture of the deep learning model affects the results that we get. And finally, some comments on how the annotator bias actually affects the ground truth generation that influences the model performance. So what is a prepreg? This is the fundamental question that we have in this project. For those of you that are not familiar with composites, composite materials are a combination of fibers reinforcement with a resin matrix, and there are different ways in which we can manufacture composites. So one of them is using a sequence of plies of this specific component called prepreg, in which the fibrous reinforcement has been previously pre-impregnated with resin. Because of that, when we do the laminate using prepregs, we can distinguish different phases. So one of them is called dry areas. These are the fiber bundle with air. Then we have the resin matrix around this fiber. Then also we have the resin impregnated fiber areas. So those fibers that have been fully impregnated with resin during the manufacturing process of the prepreg. And then we have the interlaminar voids that are normally caused during the layup of the laminate. So this is the theory, and this is the uncured state of the prepreg laminate. So before it undergoes consolidation and curing. So this is the theory, but in reality we have so in reality, it depends a lot on the distribution of the dry areas and the voids, depending on the material that we have. So the initial distribution will differ a lot because of different factors, such as different material suppliers, different batches of the same even material, different classes of prepregs. So either we are using prepregs that are going to go to the autoclave, or either they are going to be consolidated in out of autoclave process. So as a result, we can see that the dry areas, which are these gray values, are pretty different. The distribution of the dry areas and the interlaminar voids are pretty different, depending on which material we are using, and that relates to the level of impregnation on the void distribution in the materials. So actually characterizing the different phases that we have in this composite, in this laminate, is a pretty critical step during the manufacturing and during the analysis of the mechanical performance, or the final mechanical performance that we have in our composite material. And why is it important? Because if we are able to fully characterize or accurately characterize the different phases, we will be able to fit numerical models with better data. We'll be able to provide or to have a really good indications of the level of impregnation and how it relates with the final properties of the material. And also it will allow us to determine or to proceed with different quality control processes, just to quantify the differences between batches or even different materials. So now we are interested in the accurate quantification of the initial maker structure of composite prepregs. In order to do that, what we did was to take an uncured sample, put it on the CT scan at the NCC, generate the micrograph of the uncured laminate. In this uncured laminate, we can clearly see where the dry areas and where the interlaminar voids are, and then perform some phase segmentations and obtain the final volume. Important here to remember is that there are the dry areas can display a wide range of gray values depending on the amount of air that they contain. And this is really important because that will determine the accuracy or the performance of the phase segmentation. For example, we have dry areas that are displayed with darker values, and that means that they contain a high portion of air. Where there are others dry areas that are less bright and less dark, because they are mostly formed by fibers and a less portion of air. So that will actually influence a lot how accurate the segmentation process is. So now the main question is, how can we actually separate the different phases? So we tested two approaches. The first one is using thresholding. Thresholding is a really well-known method, and it works really well in a wide range of applications. We used two different approaches to select the threshold. Here in the histogram, we can see where the peaks corresponding to each phase are. So here we have the peak corresponding to the grayscale, to the gray values of the voids, the gray values of the dry areas, and also the resin impregnated areas or the resin matrix. One approach is, if you're familiar, is similar to the ISO 50. So we select the middle gray value of two peaks and we place a threshold. And the other approach is just taking the minimum gray value between two consecutive peaks. So these are two automatic processes that do not require manual or visual identification, which can be a little bit subjective. Then we use deep learning. And in this case, we use convolutional neural networks. In a sense, these convolutional neural networks is a collection of layers that are connected in specific ways. And in total, they have, in this case, millions of trainable parameters that actually learn the phases of interest and can reproduce this learning into unknown data. So the idea how it works is that the neural network will take an original image and some ground truths, and it will compare iteratively the predictions to the ground truths that it's provided until it reduces the error. So these are the two approaches that we used. Let's see some results. So just before we move on to the results, comment how the training of the deep learning model was performed. In this case, we selected random patches across different slices within the scan. The way we ensured that these patches included a wide range of void shapes, void sizes, dry area intensities, etc., so that it would account for a big variability within the train set size, so that they can replicate into a much larger scans. Also, we use patches instead of using the full size tomogram because it's a pretty labor intensive activity. And we actually demonstrated, and there are some papers demonstrating that this approach is perfectly viable as well. As I said, now we have to generate the ground truths, and generating the ground truths is a high effort activity. We have to manually delineate where the voids are, where the dry areas are. And then once we have our set of images, we evaluated the deep learning performance using only 25 images, 50 or 100 images. We trained our models, we trained 3 models, and then we applied the models to segment the full tomograms. So these are the main visual results comparing thresholding to deep learning. What we can see at first view is that thresholding is pretty noisy, especially in the segmentation of dry areas, which are in blue. Of course, we can improve the results by implementing some post-processing, removing some noise, etc. But there are some things that cannot be achieved using thresholding. One of them is the dry areas identification containing a high portion of air. And why thresholding is not really able to do that is because the gray values are really similar, if not the same, as those of the voids. So it will consistently identify them as being voids. So there is a big, that is a disadvantage of thresholding in this specific application. And then the other one is the segmentation of really small voids. So thresholding completely misses them. And that is because also of ambiguous gray values. So it is not able to identify those gray values as belonging to a void phase. But when we compare these thresholding results to the deep learning, we can see that deep learning better recognizes noise. It better recognizes what a dry area is. And it doesn't matter if the dry area has black voxels in there or here. It also mitigates the problems that thresholding had in the determination of this large dry area. And it improves the segmentation greatly of dry areas containing black voxels. So, for example, in this particular area, these are the results for the deep learning model trained with 50 images, but then 100 images, this dry area was fully segmented as being a dry area. So this was for the improvement of the dry area segmentation. We can also see some improvement in the segmentation of the voids. Now we are able to distinguish small voids, small interterminal voids. And why is this happening? This happens because deep learning does not only take into account the gray values, but it also considers context, such as what is surrounding this specific pixel. It is able to acknowledge basic concepts such as corners, edges, etc. And in the result, it's able to better segment faces compared to thresholding in this particular application. So if we move on to some quantitative data, something interesting happening is that actually dry areas and intermediate voids are segmented similarly by threshold and deep learning. But then we observe that there is a big difference in the distribution that each of the methods provide. We can see that thresholding provides a lot of dry areas counts, whereas the average volume of those dry areas are really small. So that correlates with the high level of noise included in the segmentation. As I said here, deep learning and thresholding provide similar content, but the distributions, especially of the dry areas, are particularly different. Then we wanted to evaluate the performance of the deep learning models in the segmentation of different ranges of porosity. Low porosity 1%, medium porosity 6%, high porosity 25%. We use this metric, the Matthews correlation coefficient. And we observe that deep learning works really well in segmentation of small voids. Actually, it detects voids below the acceptable level of porosity, or commonly accepted level of porosity of 2%, whereas thresholding struggles a lot in segmentation of voids in those areas. Also, deep learning outperforms thresholding in segmentation, here in the segmentation of interterminal voids, and the deep learning outperforms thresholding segmentation of dry areas at any particular dry areas percentage, but they are all the same. Since dry area, we were not really focused on the percentage of dry areas, but in the percentage of interterminal voids. So this is the main takeaways, that deep learning outperforms in really small porosity volumes. Now, we presented one single architecture. It was the UNet. It's really the UNet model, or UNet architecture. It's widely used in many disciplines, and it's like the reference. But now we wanted to say, or to study if changing actually the architecture will influence or not the performance. So can we generalize and say, okay, no matter which deep learning architecture we use, we will always outperform thresholding in this application? And if it's true, what is the performance that we obtain? In order to do that, we just select different state-of-the-art deep learning architectures, and that have been applied in composite characterization, medicine, remote sensing, construction, and put it into work, train in the same fashion that we trained them previously, and evaluate the performance in the same way that we have just presented. So, just before, I want to clarify what is the definition of a deep learning architecture. And deep learning architecture depends on the type of layer that it has, and also the arrangement and the connections between them. So you have the FCMs, for example, here, or the deep lab, which is a recent architecture, and how they look like. So these are the main differences between the architectures that we used. Now some results. Here we're focusing on the segmentation of voids. We see that when we are using a training set size of just 25 images, only UNet and FC DenseNet are outperforming or greatly outperforming thresholding, where there are most of the architectures also struggle with the segmentation of small voids. As we are increasing the training set size, the performance of the deep learning start to outperform thresholding. By using the full set size, most of the deep learning architectures or models clearly outperforms the thresholding approach. So also interesting thing is the behavior of the segment. It performs really poorly, and the segmentation of large voids. And that is because it is not able to recognize the central part of large voids. Different hypotheses can be established to that, related to the architecture itself, even to the variability in the train set size. But the global result is that deep learning, when using a train set size, including a lot of variability, is able to perform better than thresholding in this specific case. Here in the dry areas, I just took the average value and the standard deviation, and we can also see that most of them, especially segment, struggles as well, but most of the deep learning approaches actually outperforms thresholding. So now, just the last bit of this presentation is how the annotator bias actually influences the deep learning model performance. And what I mean annotator bias is that in order to train a model, you have to define the ground truths. So we gave these ground truths to us, the train set images to a range of people, and ask them to generate the ground truths, manually draw where the dry areas and voids are, do the same segmentations, and then evaluate the results. So we also studied inter-annotator agreement between the ground truths and the deep learning segmentations. We can say that the deep learning segmentations are similar between them than the ground truths are. So that means that we can have a variability in the ground truths, but these variations will be somehow mitigated when we train the deep learning models. I will move a little bit faster. Finally, where are the main disagreement provided by the deep learning models? We can see that most of the models agree in the center of the areas for expert, non-experts, and voids and dry areas. But then when we look at the dry area segmentations provided by the deep learning models trained with non-expert data, we see that there is a lot of disagreement at the edges of the dry areas. And why it happened? Because these edges are really, really ambiguous, is the interface, and most of the annotators had trouble to put the limits or to draw the edges of the dry areas. When does a dry area start? When does a dry area end? So this also causes this disagreement in these locations. So now some quantitative results. Actually, despite this disagreement, the level of inter-amina voids and dry areas was comparable between two groups. So especially big differences can be appreciated, and actually the error bars actually somehow overlap between each other. So both expert and non-experts provide comparable results. And just to end, I guess. Yeah, so we can see that deep learning constantly outperforms thresholding for this particular application. For all the applications, you have to study how well it works. In most applications, thresholding works really well, but deep learning can be used as a complement to thresholding, or can tackle, sometimes it can tackle problems that cannot be addressed directly by thresholding or require a huge amount of post-processing. Also, deep learning successfully segments volumes with low porosity. Deep learning provides a sharper and cleaner result, clear segmentation of dry areas, as we have just shown. UNet was the best model among the studied models. And finally, both groups, expert and non-expert, provide a comparable segmentation of voids and dry areas, despite these differences observed in the dry areas edges. So here is a QR code, just in case you want to look at one of the papers associated to this presentation. And finally, I would like to acknowledge Rolls-Royce and IBSim-4i for their support to this project. So thank you very much.